All right, so let's go back to our demo in class. We basically had a bicycle wheel that was supported at its center, and it's free to rotate with very little friction. We'll call that negligible. And this force F represents the force of the string pulling on the wheel. It was wrapped around the wheel. And here we have the radius of the wheel, 0.28 meters. So what we're doing in this lab is trying to solve for I, the moment of inertia of the wheel. In order to do that, we're going to collect some information and fill in this equation right here. So let's go back. Momentum, angular momentum L equals moment of inertia times omega, right? Angular speed, angular velocity. Now, so change in angular momentum is moment of inertia times change in angular velocity. And we started the wheel from rest, right? The wheel was at rest, and then we pulled on it, and then you guys collected some data to figure out how many rotations it did in a certain amount of time in order to calculate the angular velocity, right? So we did that part in class. What we didn't finish doing was calculating the torque. So the change in momentum is going to be the result of a net torque being applied for a certain amount of time. Well, the only force that's applying any torque is the string force. The other forces are gravity and normal force, which act through the center of the wheel, so those don't cause it to spin. So the net torque is caused by this single force. So torque is just force times distance, right? So we need to know this force, and we do know the distance r, and then we multiply those two and we get the torque. We also need to know the time interval that that torque was applied. So let's take a look at the graph that was generated by LabQuest 3. So that my data is a little bit different than yours because I did the experiment after you left, because I did not have the original data. But your calculation, for your calculation, you should use the one that you took a picture of in class. So you can see at this point, this little section right here, there was no tension in the string, and then the tension grew, and then the tension dissipated and went back to zero. So that's when the pull began, and this is when the string became disconnected from the wheel. So we're interested in this area right here. We need the average force value across that time interval. So you can see the min force was negative 0.01, the max force was 7.45 newtons. The average force across this interval was 2.84 newtons, which would be right about here, right around 3. So imagine 2.84 being applied the entire distance, and that would form a rectangle that had an equal area to this area bounded by this curve. So we can apply an average force of 2.84 newtons across the entire time interval. Delta x is our time interval because time is plotted on the x-axis. So 2.84 newtons for 0.64 seconds. So in this formula right here, let's replace r with 0.28 meters, and the force is 2.84 newtons, and the time interval was 0.64 seconds. All right, so that's a little bit messy. So let's shrink it down so it's easier to see. So I've basically substituted into this equation right here. Our net torque is caused by RF, right? Radius times force, and then delta t, the time interval, was 0.64 seconds. So all we have to do now is replace omega with the values we got from class, from the time that it took to do a revolution. The initial value for omega was 0 because it was starting from rest. And then after you plug those values in, you can just do some math and solve for I.